So welcome all. Today we will start one-way slab designing. First we will see the concepts regarding it, and then in the second lecture we will shift to a numerical. So we are starting. It will be a little bit longer. So stay tuned. Okay. So first step one we will see step one. Okay. So step one we have to check if it is a one-way or two-way slab. For checking it, we have to Ly by Lx should be greater than 2 for one-way slab. Okay, for one-way slab. And Ly by Lx should be less than equal to 2 for two-way slab. Okay, so this is not our concern for today, two-way slab, but we are just looking on it, where Lx and Ly is the longer span. Okay, longer span, and Lx is equal to the shorter span. Okay, so this will be the step one. Step two will be, step 2 will be, let's see. Okay, so step 2 will be, we have to assume a trial depth. Okay, we have to assume depth. So how we will assume? Let's see that. We will assume by span divided by effective depth. Effective depth should not be greater than a value. Okay, so what is this a value? What is this a value? We will see that. So a value this value is for one way slab. This a value is for one way slab up to 10 mm. Okay, 10 up to 10 meter, up to 10 meter slab. So this 10 meter is the shorter span. Okay, up to 10 meter means if there are two span of a slab, it will be the shorter span if it is up to 10 meter slab. Okay, so then the value will be, see, one side we will write slab and one side we will write the a value. Okay, so we will just see what are the values for cantilever for SSB, simply supported beam. Okay, for SSB and for a continuous beam. What are the value? For cantilever beam, the value a value is 7. For a simply supported beam, the a value is 20, and for continuous beam, the a value is 26. Okay, so this is the value. This a value will be put accordingly from this chart. So everything is as per IS 456. Okay, all these values are taken from IS 456. Okay, so see, this is up to 10 meter span. So if the span is more than 10 meter, so then a value for span greater than 10 meter. So this greater than 10 meter means the shorter span. Okay, not the longer. So the a value will be these values this 720 and 26 will be multiplied by 10 into span. So the wait, so we'll write it in a different color. Hence the above values will be multiplied by 10 divided by span. Okay, there is an exceptional, that is except the cantilever slab. What is this exception? See, for this SSB, okay, for this SSB and for this continuous okay, so for this SSB and continuous, what we will do, we will multiply these values 20 and 26 by 10 into span if the span value is more than 10 meter. But for cantilever, for 10 meter slab, up to 10 meter slab and more than 10 meter slab, the cantilever value will be same. Okay, hope it is clear now. So we will go to the next step. So next step, let's see which step 2, step 3. Okay, so step 3 is step 3. Okay, so step 3 will be effective span. Okay, so step 3 is effective span calculation. We know that effective depth. Okay, so like that there is an effective span calculation. So for first we will write for SSB, simply supported beam, what will be the effective span. So we will just give me a minute, we will draw a beam. Okay, simply supported beam. So we will just draw a simply supported beam. We will draw a simply supported beam. Okay, okay, I am not drawing it at accurate. Okay, you can understand it. Yeah, so see one thing, these are the support. Okay, this part is the support and this is a simply supported beam. So now, so this is a simply supported beam. See, this one is told as this one. Okay, so this one is called as clear span. Okay, so this one is called as, say we are saying it at B1 and B2, the support width we are telling it as B1 and B2. Okay, and let's say this someone is the effective cover, and from this part this is the effective depth. Okay, so the clear span for the effective span for the simply supported beam will be, see here, L effective will be clear span plus effective depth, we are writing it as small d, or clear span clear span plus B1 by 2 plus B2 by 2, whichever of this is minimum. Okay, so the L effective will be taken as clear span plus effective depth, or clear span plus the support, both the support half. Okay, so whichever value is minimum we have to take it. So next we will see see, for this is for simply supported beam, so we once see it for the cantilever also. For cantilever, okay, lever, for cantilever, if we see, we have to draw one beam. Just, yeah, we have drawn one beam. Say this is a cantilever beam. Okay, say it is a support here. Okay, we can draw a support also. Yeah, let's say there is a support here. Okay, now this is a support, this is fixed from here. Okay, this is a cantilever, so this is, say, so this is the effective depth D, and this is the clear span. Okay, this is the clear span. So for cantilever slab, the L effective value is, the L effective value for cantilever is clear span plus D by 2, effective depth by 2. Okay, there is only one thing only for cantilever. See, this is the step 3. We will see step 4. Okay, slowly I am going, that we can understand everything. Okay, so the step 4 will be, so see, in step 4 we will calculate the load calculation. Okay, so step 4 will be a load calculation. Okay, so let's see what we will do here. In the problem, in numerical, live load will be given. Live load or superimposed load, anything can be sent. Live load will be given in kilonewton per meter square. Okay, dead load or self weight. Okay, so it dead load, or we can say it as self weight, we have to calculate. See, the slab B into D into gamma into, that is unit weight, into 1. So we have to calculate this thing. There is one very important point here we have to remember. In slab we design for width of 1 meter. Okay, or 1000 mm. Okay, that is B is equal to 1 meter. Means if we draw a diagram here, see, if we draw a diagram here, see, if this is the slab. Okay, if this is the slab, so if this is the slab, what we will do, we will design it for a width of 1 meter. Okay, as because a slab, there is a huge span, so if we take the whole, the calculation will be critical. So we take B, as we design for a strip in a slab of 1 meter, and this whatever will be the total span we will multiply with it. Okay, so here this is a very important point here in the slab. Okay, after that we have done the live load, we have seen the dead load. Now we will see the floor finish. Means if see concreting has been done, so we will not just stay like that. We can do marble, we can do tiles, we can do some wooden frame. So we have some weight of floor finish that we call as floor finish. Floor finish. Okay, so we generally assume it that the floor finish is of 1 kilonewton per meter square. We assume it as like that. Okay, so the floor finish is generally 0.5 to 1 kilonewton per meter square. What is the next step? So next step will be just total factored load calculation. Total factored load. Okay, so we can call it at WU also. So 1.5 times, we know that factored we multiply it with 1.5. So LL is live load plus DL is dead load plus FF is floor finish. So we will get the total factored load. Okay, so now we will see the step 5. Step 5. Okay, so what will be the step 5? Let's see. So mainly in step 5, we will calculate the moment and the shear force. Okay, so we will calculate maximum bending moment and shear force. Okay, so let's see what are the thing. So if we first calculate for a simply supported beam, everybody we know that bending moment maximum is WL square by 8. So here WU, so this is WU, L will be L effective. Okay, L effective WL square by 8. Okay, and for a simply supported beam, the shear force maximum, we know that it is WL by 2. So here will be WU L effective by 2. Okay, so next thing we have seen the simply supported beam. So next will be the cantilever. Okay, so for cantilever, this thing we have done in strength of material. Okay, so for cantilever, the bending moment maximum is WL square by 2. It is WL square by 8 for simply supported beam, and for cantilever it is WL square by 2. Okay, WL square by 2. And shear force maximum is W by 2, just W by 2. Okay, so this is step 5. Now we will see step 6. Step 6, let's see. Now we will check for moment, and from this moment formula we will calculate the D required. Okay, so we will calculate the D required. So see, first we have assumed the D in step 2, I think. See here, we have assumed the D, so this you can call is as D provided. Okay, D provided one first we have assumed. Now we will calculate the D required. How we will calculate? See, so we know the moment formula, so you can write it here. Check for moment. So previously we have read one formula, that is ultimate moment formula is QBD square, where you can if we just one revise for if the Q value, for Q value depends on mainly the grade of steel. Okay, so if we just once see the values, yeah, let me see the values for AFE 250, okay, for AFE 415 and for AFE 500. See, for AFE 250 the value is 0.148 FCK. For AFE 415 the value is 0.138 FCK, and for AFE 500 the value is 0.134 FCK. Okay, so these are the values of Q. So from here what we will do, we will just find out the D. So D will be, see, M divided by Q into B and root over this value. Okay, so this so this D will be D required. Okay, now we will check one thing, that is if D required, the value we got from this above is mainly D provided should be greater than this value. The assumed depth what we have taken earlier should be greater than this value. If this condition is okay, then design is okay. Design is okay till now. Okay, so we will see the next step. The next step is step 7. Step 7. So let's see. So in step 7 we will calculate the main reinforcement. Okay, main reinforcement we will calculate. So there is an universal formula to get the area of steel, that is 0.5 FCK divided by Fy bracket 1 minus root over 1 minus 4.6 mu divided by FCK BD square bracket B into D. Okay, so this is an universal formula to get out the area of steel, but we have to check after the area of steel getting from here, we also have to check the minimum area of reinforcement, that is from IS 456. Okay, so check for minimum area of reinforcement. Okay, so for mild steel, a minimum is equal to 0.15 percentage of cross section area. Okay, that is BD, cross section area, and for HYSD steel, steel, a minimum will be 0.12 percentage of cross section area. Okay, so we have to check this also, the minimum steel requirement, area of steel requirement. Okay, now this AST main, that is that we have calculated should be greater than is equal to AST minimum. Okay, so one thing we can remember is also that maximum area of reinforcement is 4% the cross section area of 4% the cross section area. Okay. So now we will go to step 8. So step 8, what is step 8? Let's see. So in step 8 we have to calculate the spacing. We have calculated the area of the main bar. Now we have to calculate the spacing. Okay. So see, the spacing will be, how we calculate the spacing? Say S is the spacing is equal to 1000. We calculate for 1 meter. Okay. So 1000 divided by number of bars. So we can write it also like that. 1000 divided by, how we calculate number of bars? Total area AST of main bar divided by area of one bar. So pi by 4 into 5 square. Okay. So also we can write it as 1000 divided by AST main into pi by 4 5 square. Okay. So in this way we will calculate the spacing of one bar. Okay. So there is also an IS code provision for the maximum spacing, that is a maximum spacing for main bar. Okay, for main bar, what is that? Should not be greater than, okay, 3 times the effective depth or 300 mm, whichever is minimum. Okay. Now we come to the distribution bar. Okay. Now we come to the distribution bar. So step 9. So now step 9. Okay. Step 9. So step 9 is distribution reinforcement. Okay. So step 9 is distribution reinforcement. Distribution reinforcement. So let's see. So we have to take one grade down. Okay, the bar, the dia of the bar, in which we have taken the main reinforcement. If we taken the main reinforcement as 10 mm dia, okay, so we will take 8 mm dia for the distribution bar. Okay, as because same dia bar is not required, greater is not required at all, but same dia bar is not required. Okay. Now you can calculate the spacing. Okay, so mainly the area of steel will be same. Okay, the area of steel will be same, as because you can see it here. See, mu moment is same, BD is same for the same slab. Okay, the area of AST will be same, just the value of spacing will be different. Okay, so spacing for distribution reinforcement. Okay, spacing for distribution reinforcement. Let's see, just a very easy thing. Yes, we have to calculate same thing, 1000 divided by AST. We are writing it as distribution into pi by 4 phi square. If someone says how, if the AST is same, if here the AST is same, so how the spacing will change? Mainly the dia of the bar, we will take it a different. If in this case, in say in spacing for, we can write it here for main bar. Okay, so for main bar, if this dia we have taken as 10 mm, and for the distribution bar this dia you have taken it as 8 mm, then the spacing will change. Okay, this is the main difference of finding it out. Okay, so there is also an IS provision. So max spacing for distribution bar. Okay, distribution bar. So what is that? It should not be greater than 5D or 300 mm, whichever is minimum. Okay, so now there is the last step, that is we have to check for shear. Okay, just it is a check, nothing that, just we have to, the designing is complete till this step, we have to just check for shear. So check for shear. So we have to find out the nominal shear stress, that is tau, as we know. Okay, previously also tau vu, we have to find out that, that is tau vu is equal to vu divided by, this is u. Okay, vu divided by b into d. Okay, so this factored shear force will be, for simply supported beam you have to calculate it. Okay, the shear force, maximum shear force, and after that we have to calculate the design shear stress. Okay, so design shear stress. So we know that we get this tau c value from table 19. Okay, table 19, that depends on percentage of steel and 1% of steel and 2 grade of concrete. Okay, grade of concrete. So in mainly slab, we make the slab safe in shear by increasing the depth. Okay, nothing more than that. We just increase the depth of the slab and just we make it safe in shear. Okay, now we have to just compare the TC greater than TVU, and design is safe in shear. Okay, just this thing we have to do. Now we have to do another check. The check is step 11. Step 11, what it will be? So it will be a check, that is check for deflection. Mainly we design slab for deflection. Okay, that is check for deflection. Okay, so how we will calculate the L by D actual less than is equal to, should be L by D permissible. I know that it is not understandable, this thing. I am just explaining it. Wait, see, L by D permissible, mainly this L by D is the value, the A value. Okay, so this L by D is the A value. Okay, like we saw now, the L value for cantilever is 7, for simply supported beam is 20, up to span 10 we are telling. And this L by 2, how we are getting? L will be given and D we have assumed it, so this we have to do it. So L that is given and D that we have taken from the trial. Okay, or assume it. So from this value you have to just check it is within the permissible limit or not. Okay, and then we have to tell that hence design is safe in deflection. Okay, then another step will be just detailing. Okay, so detailing we will see it in the numerical part. Okay, when we will do the detailing we will see it. So I am ending up the lecture here. Thank you. So I meet you in another lesson in which we will do the numerical of one-way slab designing. Thank you.